All right, section 11.2, and we're going to be doing some more chi-squared statistic, but in this time we're going to do the chi-squared test for homogeneity and the chi-squared test for association slash independence. So here we go. Two sample Z procedures of chapter or module 10 allow us to compare the proportions of successes in two populations, or for two treatments. What if we wanted to compare more than two samples or groups? Or generally, what if we want to compare the distributions of a single categorical variable across several populations or treatments? So we want to see what's happening with lots of different things going on. So we need a new statistical test, and this one is going to be when you have data basically all in a two-way table. So two-way tables have more general uses than comparing distributions of a single categorical variable. They can be used to describe relationships between any two categorical variables. So in this section, we're going to see those relations. Okay, so chi-square test of association, or also called a chi-square test of independence, is used to determine whether two variables are independent or not. A chi-square distribution is always skewed to the right, just like we've already seen, and gets closer to the norm as the degrees of freedom increase. Here we can use matrices from the two-way tables. And an important distinction, the goodness of fit test compares only one variable with two populations, the expected and observed. So that's why you just have the two lists. But here, the test for association or independence here compares two variables within one population. So you can have the whole table going on. Okay? So the test procedures described in this lesson is inappropriate when the following conditions are met. You have a simple random sample, your variables are categorical, you have your table going on, the expected frequencies of everything in the table is at least 5, or you could say 20% is at least 5 and all are at least 1. I'm fine with however you want to say that. Okay. This approach consists of 4 steps.
As you get your grades all posted and completed, check with your department
Sorry.
head, let them know that you completed that process. Also, Fazia, may I see you in the office?
Okay, so that wasn't me. State the hypothesis, formulate an analysis plan, and analyze sample data and interpret results. Here we go. Let's do this example. Market researchers suspect that background music may affect the mood and buying behavior of your customers. One study in a supermarket compared 3 randomly assigned treatments: no music, French accordion music, and Italian string music. Under each condition, the researchers recorded the number of bottles of French, Italian, and other wines purchased. Here is the table that summarizes the data. This is very interesting. Okay, calculate the conditional distribution and proportions of the type of wine sold for each treatment. Make an appropriate graph for comparing the conditional distributions in Part A, and are the distributions of wine purchases under the 3 music treatments similar or different, and give appropriate evidence from Parts A and B to support your answer. All right. Oops, wrong one. So when no music was playing, the distribution of wine purchased was: French was 30 out of the 84, Italian was 11 out of the 84, and let's see, what do we have? The other was going to be 43 out of the 84. Here you can see the proportions when the French accordion music was playing. And here, when Italian string music was playing, here are your distributions. Here you can kind of see a nice little histogram going on. Okay, so the type of wine that customers buy, it does seem to differ considerably across the 3 music treatments. Sales of Italian wine are very low when French music is playing, but are higher when Italian music or no music is playing. French wine appears popular in this market regardless, but selling well under music conditions, but notably better when the French music is playing. For all three music treatments, the percent of other wine purchases was similar. All right. So the problem of how to do many comparisons at once with an overall measure of confidence in our conclusions is common in statistics. This is the problem of the multiple comparisons. Statistical methods for dealing with multiple comparisons usually have two parts, an overall test and a follow-up analysis. The overall test uses the familiar chi-squared statistic and distribution. So here, why that's not moving. Anyway, perform a test. So here our null hypothesis is there's no difference in the distribution of categorical variable for several populations or treatments. And make sure you're writing this in context of the problem. We'll get to that. And your ha is there is a difference in the distribution of categorical variables for several populations or treatments. Remember your null is always no difference. Equals, right? No difference. Okay, we compare the observed counts in a two-way table with the counts we would expect if the null were true. I don't know what is going on. Why it's being silly. Something's happened. Ah! It's really annoying. See if I write something and then try to go. Oh, gotta love technology sometimes. It is completely froze. What the heck? All right. Don't know what that was about, but here we go. Finding the expected counts is not that difficult, as the following example illustrates. So here our null hypothesis in the wine and music experiment is that there's no difference in the distribution of wine purchases in the store when no music, French accordion music, or Italian music was playing. To find the expected counts, we start by assuming that the null is true. We can see from the two-way table that 99 of the 243 bottles of wine bought during the study were French wines. So we could see if the specified type of music that's playing has no effect on wine purchases, the proportion of French wine sold under each music condition should be about 99 out of 243. So the overall proportion of French wine bought during the study was 99 over 243, so the expected counts of French wine bought under each treatment, we're going to take our 99 out of the 243 and multiply by the 84 for the none. So we take our 99 out of 243, multiply it by your 84, and we can see that this would be 34.22. Okay, so here if I take our 99 out of 234 and multiply it by the 75, I can see this expected count was 30.56 and 34.22. And we can continue to do this. So the values in the calculation are the row total divided by the column total, and then multiplied by the table total. Or no, hold on. Are the row total divided by the table total multiplied by the column total. There we go. So an easier way of thinking about that is you're going to take each of the individuals, so you can take your column total, table total, multiply those, and then divide by the overall table total. So that's really the easiest way to kind of find this expected count. So if I wanted to find the French, I would take column times row divided by overall. If I wanted to find it for this guy right here, I would take 75 times 31 and divide by 243. So you just have to do that for each of those 9 things to find your expected counts. All right, so we have to check all of our conditions. So all of the expected counts when we do this have to be at least 5, or you can say all are at least 1 and 20% are at least 5. You have to be random, and it said it was random. And you have to be independent. So if a customer buys several bottles of wine at the same time, knowing that one bottle is French wine might give us additional information about the other bottles bought by this customer. In that case, the independent condition would be violated. But if each customer only buys 1 bottle of wine, this condition is probably met. So since we can't say that we know for sure if it's independent, we're going to proceed with caution. And then we can go find our chi-squared statistic, just like we did in the goodness of fit test. Now make sure that you do not include the overall totals going on, okay? This is only for those 9 different things. So you can see what I mean is right here, okay? Only include those. Do not include these guys when you go do the chi-squared statistic. You're not including the totals. Okay. All right, so here were all of our expected counts. Again, we could see what they were, all above 5, so we're good to go there. You can find your chi-squared statistic, and I got it to be 0.52. And, oh no, that was for just one of them, sorry. Okay, the overall chi-squared statistic was 18.28. I was like, man, those are really close together. But, okay, sorry, that was just for one of them. Okay, so for all, when you add all of them up, you get 18.25. So another way you could do this is in your calculator. If you go to the matrix button, select edit, and go to matrix A. So in matrix A, you're going to enter your 3 by 3. So remember, we don't include. So put all of your observed counts into matrix A. And they were basically these right here. So put those into matrix A in that 3 by 3 matrix. Okay? And if you need help with matrices, just let me know. I'll help you out. But I think most of you should have that skill down. So then go to your stat test and choose your chi-squared test. Here for your, I'll tell you which one it is. That one's kind of vague. Stat test. And it's faster if you go up in this one. And it's just C, chi-squared test. So you have the chi-squared test, you have the chi-squared goodness of fit test. So we want the chi-squared test. So then where it says, oops, sorry, stat test, chi-squared test. So then where it says observed, put the matrix A, and it should probably already be there. And then in matrix B, or expected, you're going to put matrix B. Now do not, okay, do not do anything. Don't like go put anything into matrix B. The calculator is actually going to perform it and go find all of those expected counts for you. It's pretty cool. Okay, so go hit, just put B in there, but don't put anything into that matrix B. Then when you hit calculate, you can find the chi-squared statistic and your P. So now if you go back to matrix, go hit edit B, or even just hit B. Go look into what's in matrix B, and guess what you're going to find? All of these, even though you didn't put them in there. That test just put them all in there for you. So pretty cool. Saves you a lot of work, but you still need to know how to find them by hand. All right, so chi-square test of association or independence here. So I want to determine if there was a relationship between smoking status and socioeconomic levels, and researchers categories 356 male employees here. So here's the high school or the socioeconomic level of high, middle, and low, and if they're a current smoker, former smoker, or never smoked. So again, this is a 3 by 3. You could have lots of options. You could have a 15 by 4. Okay, so go find the expected counts. And we're good to go here. All of these are at least 5, so we don't even have to check the other part. State your null and alternative hypothesis. Check your conditions. And you could go put it in the calculator. You could actually put it in the calculator first and then check your conditions. So you could see, excuse me, about that expected counts part, so you didn't have to do it by hand. But I would suggest always knowing how to do it by hand, because AP will sometimes just ask you what's the kind of like procedures of things. Okay? And then put your conclusion. Here our p-value is definitely less than our 0.001. So you're really confident here to, it's very statistically significant to reject your null and conclude an association exists between smoking status and the socioeconomic status in the population of federal male employees. All right, so now let's look at the chi-square test for homogeneity. When the random large sample and independent conditions are met, the chi-squared statistic calculated from a two-way table can be used to perform a test of there is no difference in the distribution of categorical variables for several populations or treatments. P-values for this test come from a chi-square distribution, and here you're going to have to know your degrees of freedom, number of rows minus 1 times number of columns minus 1, and this new procedure is known as the chi-square test for homogeneity. So weird. Okay, there. So suppose the random large sample size and independent conditions are met, then you can use this chi-square test. And here you put in your null that there is no difference in the distribution of categorical variables for several populations or treatments. And your alternative is there is a difference. Okay, so start by finding the expected counts. Then you can put in your degrees of freedom and look at the p-value of the area to the right of the chi-squared under the density curve. Okay, here it is just again. Make sure you state the hypothesis in context of the problem. So the p-value represents the chance of the data occurring given that the variables are independent. So let's look at this example. Does music influence purchases? Earlier we started a significance test. There is no difference in the distribution of wine purchased at the store, and there is a difference. Okay, so we decided to proceed with caution because although the random and large sample size conditions are met, we aren't sure if they are independent. So we're going to calculate our chi-squared test, or chi-squared statistic, and we can find our p-value using the table. So do your degrees of freedom. So you have 3 minus 1 times 3 minus 1. So your degrees of freedom are 4. So it's going to be somewhere between 0.0025 and 0.001. So the small p-value gives us convincing evidence to reject the null and conclude that there is a difference in the distributions of wine purchases at this store when no music, French accordion music, or Italian music is played. Furthermore, the random assignment allows us to say that the difference caused by the music that's played. That's pretty cool. All right, random digit dialing telephone surveys used to exclude cell phone numbers. If the opinions of people who have only cell phones differ from those of people who have landline service, the poll results may not represent the entire adult population. The Pew Research Center interviewed separate random samples of cell phone only landline users who were less than 30 years old. So here's what they found about these people. So we want to perform a test if there's no difference in the distribution of the party affiliation between the cell only and the landline populations, and there is a difference. between these two. And since it didn't tell us, we're going to go ahead and use a 95% confidence, so our alpha will be 0.05. We're going to do a chi-square test for homogeneity. Is it random? Yes. Do we have large enough samples? So here, all I did was put that into my test and found my B to make it a lot easier for me. And is it independent? Yes. Find our chi-squared statistic, find our p-value. Again, you can find this in your calculator by doing your chi-squared test. And we got a p-value of 0.19989 approximately. All right, so the follow-up analysis, the chi-square test allows us to compare the distribution of categorical variables for any number of populations or treatments. If the test allows us to reject the null hypothesis of no difference, we then want to do a follow-up analysis that examines the differences in detail. Start by examining which cells in the two-way table show large deviations between the observed and expected counts. Then look at the individual components to see which terms contribute most to the chi-squared statistic. So here, like when you did each of those individual, that's why you want to know how to do it by hand as well. You could look and see. Okay, which ones would contribute most to the chi-squared statistic? Was this guy, that guy, right? Looking at the output, we see that just 2 of the 9 components made up the chi-squared, made up about 14, almost 77% of that chi-squared statistic. So we are led to a specific conclusion. Cells of Italian wine are strongly affected by Italian and French music. Okay? So that's something like you really want to do a follow-up in and to kind of look at each of those individual components. Okay, so many students will incorrectly state the HA as all the proportions are different. So make sure you just say at least one. Okay. And I'm going to see if you guys can do this one. You can pause at any time. Okay, so here was the end of that. And if you have any questions, let me know. Here's another one if you want more practice. Okay, so the chi-square test for that association independence, we often gather data from a random sample and arrange them into a two-way table to see if 2 categorical variables are associated. The sample data are easy to investigate. Turn them into percents and look for a relationship between the variables. Our null hypothesis is that there is no association between the 2 categorical variables. The alternative hypothesis is that there is an association between the 2 variables. For the observational study of anger level and coronary heart disease, we wanted to test this hypothesis. No association between the 2 variables means that the values of one variable do not tend to occur in common with values of the other. That is, the variables are independent. An equivalent way to say the hypothesis could also be this as below. So when you're dealing with association or independence, you could set it up as either one of these 2 hypothesis. So that's why you could say that there is no association, there is an association, or they are independent or they are not independent. You can get full credit for either way. All right, so here's one if you want to do for association. You can set up your null and alternative. Check your conditions. Calculate your statistic. Find your p-value. And then state your conclusion. All right, so both of the chi-square tests, the test for homogeneity and the test for association, start with a two-way table. So how do you know the difference, right? They even calculated the test statistic, degrees of freedom, the p-value exactly the same way. So the questions that these two tests are answer are what's the difference. Okay, so a chi-square test for homogeneity tests whether the distribution of a categorical variable is the same for each of the several populations or treatments. Whereas the chi-square test for association or independence tests whether two categorical variables are associated in some population of independence. So instead of focusing on the question asked, it's much easier to look at how the data were produced. If the data come from two or more independent random samples or treatment groups in a randomized experiment, then do a chi-square test for homogeneity. If the data come from a single random sample with the individuals classified according to the two categorical variables, use a chi-square test for association or independence. And this is just another way to say some of that. Let you read through it. So if you're thinking homogeneity and independence sound the same, you're nearly right. The difference is a matter of design. In the test for independence, observational units are collected at random from a population, and two categorical variables are observed for each unit. In the test for homogeneity, the data are collected by randomly sampling from each subgroup separately, say 100 black, 100 whites, 100 American Indians, and so on. So the null hypothesis is that each subgroup shares the same distribution of another categorical variable, say chain smoker, occasional smoker, non-smoker. The difference between these two tests is subtle, yet very, very important. So in the chi-square test of independence, two variables are observed for each observational unit. In the goodness of fit, there was only one. So don't forget that goodness of fit as well. That's when you just have the two lists. All right, so you made it through chi-squared. You only have one more module to go. Here's the summary. And then here's some AP examples. So let's see if you can do this one and then pause. And you can check pretty much everything we've been doing. Nice and big for you. When you don't know alpha, then you can always use 0.05. All right. See you in Module 12. Have a good day. Good luck on your test.